Oh, all right, there you go. Just to get it closer to myself. So, hi everyone, thank you for coming to our talk. A brief history of math writing. My name is Alfonso, this is Emily.
Hi.
So, what exactly is this presentation about? And what is this math writing that we speak of? And so we chose this term, math writing, because it's perfectly ambiguous. And so it kind of lets us talk about whatever we want. And for the purposes of this presentation, that's going to be anything that's related to math and writing in general. So we hope that you, the audience, can walk away with some new ideas, regardless of what your own writing is about, after hearing our presentation.
But first, before we talk about math writing, let's talk about writing. So writing used to be very difficult, even for the few people that knew how to do it. And reading was even harder. We have a lot of improvements in modern writing that make reading easier. For instance, we have spaces between words, that is. We have capital and lowercase letters, and we don't just use them one at a time, we use them at the same time for readability and scannability. We have punctuation. Romans did sometimes use dots between their sentences. You might be able to make it out here. But other than that, readers were totally on their own. There were no commas or colons or dashes, parentheses, just context. And typography, oh my God, typography. So, kerning, fonts, colors, and beyond that, new things like automated syntax highlighting or hypertext that lets you emphasize things in all different kinds of ways. And possibly the biggest advantage that modern readers and writers have, of course, is cheap, abundant paper and basically infinite digital storage. So parchment used to be so expensive that you had to scrape it off and reuse it over and over again. And in that context, of course they couldn't spare room for spaces and punctuation, right? So basically what we're saying is that if writing was the first information technology, then spaces, cases, and punctuation were the first UI improvements. So think about that for a minute. What does it really say? Writing is actually an information technology, and we don't think of it that way, but it is. So, and like other technologies, writing has gotten better over time based on how we're using it and what we need from it. So in ancient Greece and Rome, in the examples we looked at, for instance, academic culture was more about oral history and memorization. So writing wasn't so much for the pleasure of reading or interacting with, as much as it was for keeping a record or using it as a visual aid for memorization. But things changed, and culture changed. Paper became available, codices, and eventually people began to use written language as a supplement to spoken language, not just as a supplement for spoken language, but as a supplement to thinking.
So one of the themes that we want to get to this presentation is that language and notation are tools for thought. And we were partly inspired to do this presentation because we saw Bret Victor, and in his Media for Thinking the Unthinkable talk, he says, thinking tools adapt unthinkable thoughts to our human minds. Two of the greatest such tools are writing and mathematical notation. Now, Bret Victor likes to talk about UI improvements, and following that kind of train of thought, we can think of the first UI improvement in math writing was numbers. Now, let's ask ourselves, why do we even need numbers? And so we can only perceive 37 things at a time, cognitively speaking. So using dots or lines or symbols to keep count doesn't work well for too long. And if you try counting with your fingers and toes, well, you're going to run out of those pretty soon. So we can probably devise a tallying system and count by 5s or 2s or 10s. But that only gets you 5 or 2 or 10 times more information. And what if in the ancient times, you're quite the sheep impresario, and at some point, you won't be able to keep tally of your sheep. Now, we did invent number systems at some point, and those early number systems were generally extensions of that tallying concept. And they were good for keeping score and counting sheep, but even basic arithmetic was very difficult. Now, an improvement on this was the invention of the abacus, which takes tallying to the next level by adding place values. Now, this is, of course, still a tallying system, but now instead of needing different symbols to increase the value of the bead, now we can increase its value by its relative place, in the abacus. So this was a great piece of technology for its time.
Okay. So, speaking of abacuses and Roman technologies, let's talk about Roman numerals. That's another piece of Roman technology. And we see them almost every day, so they must be good for something, right? But they do have a lot of problems, and they actually a lot more problems than I initially realized when I started putting this together. So you can think of this as all the ways that notation can be just terrible. So first of all, Roman numerals are very long. They're actually fractal in length, so there's a self-similar and repeating pattern that slowly increases forever. Whereas Arabic numerals, on the other hand, have this nice orange graph that flattens out over time. So that means that the larger a number is, the fewer digits you need to represent it relative to the size of the number, which is pretty cool. Roman numbers are irritatingly indistinguishable from letters, so that can lead to all kinds of confusion. And they're full of nonsensical possibilities, so there's all kinds of things that you can write that don't make sense, which is very inefficient. And there's no such thing as a nonsensical Arabic numeral, if you think about it. Now, the biggest problem with Roman numerals, and hieroglyphics say, is that there are multiple ways to write down a single number. So there's only one way to write the idea 18 in Arabic numerals. It's a 1 and then it's an 8. But there's at least 3 ways to write it down in Roman numerals, more if we get creative. So it's clear to me based on length and legibility that this third option is the best, 10 plus 5 plus 3. But nothing's really stopping me from writing it as 15 plus 3 or 18 ones. Or we also have this subtractive system, so why can't I say 20 minus 2? There's really no reason. It's a matter of style, isn't it? So basically, good notation shouldn't require a style guide. So if we want to look at this from a nerdier perspective, from our perspective, we would say that if you define a writing function from the space of all possible integers that you can think of into the set of all possible Roman numerals that you can write down, then it's not even a function in a mathematical sense, because there's more than one way to write each number. And even if you did define a precise rule for how to write down each number in a single way, then it's still annoying because it's not what we call a surjective function. There's all these additional combinations of Roman numerals that don't get mapped to by an integer. And conversely, if we try and define a reading function from the set of all possible numerals that you can observe to all the meanings you can infer from them, it's still not a function, because remember, Roman numerals got reused from letters, so they're not well defined. A single character could represent a number or a letter or an abbreviation for something. We really don't know. So to sum it up, Roman numerals do a great job at counting. They're good for chiseling on buildings and apparently people, but they're hard to write, they're hard to read, and they're useless for doing any arithmetic. That's what an abacus is for. And they're definitely not good for complex math. Just imagine trying to do algebra with them, for example.
Speaking of algebra, so if you look at early algebra, if you thought you hated word problems, well, old math problems used to be word problems. So let's take an example. So something from Diophantus' Arithmetic of Book 1, Problem 6, and this problem states, to divide a given number into 2 numbers such that a given number fraction, the first number exceeds given fraction, and oh boy, let's just skip to the solution on this one. You get that. Okay, it's not gonna scale. It's not gonna work out very nicely. So now let's apply the magic of modern mathematics to arrive at something like this. So now we've represented that same problem as a system of linear equations, and certainly you can agree that it's easier on the eyes. Now, it may still be difficult to solve, but the solution can be arrived at very procedurally. You do the simplification step, you do the substitute step, you solve for y, solve for x, and you have your answer. So it's fair to ask, why is this any better? I mean, this is a nicer, compact representation of the problem, but there's nothing really wrong mathematically with the way Diophantus did things. But this notation unravels a new concept, and that's variables. Now think about this. We've introduced placeholders, and this makes more complex and abstract thought possible. You can now start creating mental structures using placeholders where you're missing information, and as you basically fill in the blanks, so to speak, and as you crack the problem. Now this sort of thing would be hard to do using Diophantus style, and we also get nicer things like operators. This helps us easily identify different actions like addition and subtraction in our case here. And we also get hints from structure. So now we can move the symbols around and imply actions and operate them to arrive at more obvious ways to solve the problem. And it doesn't stop there. The invention of more abstract notation made it possible to express ideas like the calculus, which then required even more complex structures like vectors, which give hint at the idea of dimensions, physical or abstract. So they're a foundation of modern physics. And then we have set theory notation, which was a precursor to Boolean algebra. And Boolean algebra, as you may or may not know, is the underlying structure of computational logic. It provides logical operations to bits, and you do enough of these logical operations sufficiently fast, and you have yourself a computer. So we come back to this idea, right, that language and notation are tools for thought. And George Boole, the inventor of Boolean algebra, perhaps realized this too when he said that language is an instrument of human reason and not merely a medium for the expression of thought, is a truth generally admitted. Or maybe not so generally admitted, which is why we're talking about it now. So we see a chaining of events happening here where one thing made the other thing possible, right? Now, these are the kind of things that the smartest people in the world could barely wrap their heads around without this sort of notation. And these problems are now formulaic and easy to grasp for the average 12-year-old with enough practice. So without the right language and notation, these ideas will still likely be possible, but they may not have escaped the minds of the extraordinarily smart, and they certainly wouldn't be in high school classrooms around the world now.
So like Franz is saying, without good representations, abstract ideas are more difficult to understand, right? And we can take that a step further and say, well, things that are hard to understand, are also harder to believe, right? So that leads us into our next question. How can we make these complex ideas like math, that are so complex and so abstract to the point of almost being incredible, into ideas that are credible? Well, that's a very tough question, possibly very philosophical depending on how you want to look at it. But it's basically what we're going to try and talk about for the rest of the presentation, which is the concept of proof in mathematical writing. So what makes people believe things at all or not believe things, and what's required to prove that something is true? So let's start by looking at a very small and simple example. Why do people doubt evolution, despite massive amounts of scientific evidence supporting it and natural selection? Well, I would argue that it's because the proof of evolution is what we would call an inductive proof. Or in other words, for the same reason that this inductive proof is wrong. Prove that all numbers are smaller than 1 million. Well, that's easy. 0 is less than 1 million, 1 is less than 1 million, 2 is less than 1 million, 3 is less than 1 million, so on and so forth. I could do this all day, but I don't want to, so obviously I'll just conclude that all numbers are smaller than 1 million. And so this is the basic difference between math and science that we have illustrated here. This inductive proof clearly doesn't fly in the mathematical sense, but it's a rough and very insulting approximation of how science works. So you make a hypothesis, you find evidence to show that your hypothesis works, and then that hypothesis is good until someone else proves it wrong. So what I'm trying to say is that people who doubt evolution are thinking to themselves, yeah, sure, there's a million pieces of evidence, but first of all, I'm not sure if that's enough. And secondly, who's to say that sooner or later, someone won't go ahead and count to 1,000,001, so to speak, and then the whole theory falls apart. In other words, from a math standpoint, science never proves anything. But you're probably thinking to yourselves, well, what the hell does she mean by prove? It depends, right? And that's a good point. So there are different standards of proof, depending on the context. So in a courtroom, to prove something, you have to show that it's true beyond a reasonable doubt. And where you are defines, what country you're in or what courtroom you're in. It depends what reasonable means. And really, what reasonable means is different in the mind of every person, because that's just how words work. In science, for something to be considered true, it has to be true by consensus. So mainly the consensus of the data itself, but also consensus of prominent scientists, especially in very narrow fields. And it just sort of has to work this way because of its inductive nature that we talked about before. So math, on the other hand, we generally think of as requiring a much more rigorous standard of proof. And it depends on who you ask. Mathematicians would debate about what exactly that standard is. But I think the best definition is a simple one, even though it doesn't really sound very rigorous. It's that for something to be mathematically true, it has to be reproducible by any qualified reader. And I hope that rings some bells with those of you who write documentation, in that that's just much harder than it sounds. So let's talk about how we do that. Oh, and I just wanted to mention for a second, there is a branch of mathematical logic that defines what a proof is very precisely, but it's not relevant to our discussion because we're only talking about natural language proofs today. Okay, so let's say this another way. Science uses induction to make a prediction. You take a measurement, you make a prediction, you measure again to see if you did okay. Math, on the other hand, uses deduction to make a proof. So let's break that down. What's deduction? What's a proof? So starting with a proof. It depends again on who you ask, but the simplest possible definition I can think of is something that shows us how two statements logically connect. So we have a B, where we're going, we have an A, and the proof shows us how to get between the two. More specifically, you do a proof by starting by stating what you want to prove. So you want to know where you're going before you slog through all the details to get there. Then you define your terms and outline your assumptions that you're going to start from. And finally, you use deductive logic to reason from your assumptions to reach your conclusion. So now we have to address what's deduction. So deduction is a way of thinking about things, a process of reasoning. It's also informally known as top-down logic, because any argument that you make has to be based on definitions and premises that you have to define up front very carefully. In other words, we get to make up our own world and then write our own rules about it. So for instance, I could say that we're going to assume for the rest of this presentation that all dogs have 3 legs. And yes, I realize that most dogs have 4 legs, but for our purposes, we're going to define a dog as having 3 legs. So if I ask you later on in the presentation how many legs 5 dogs have, you would have to say
15.
Good. So this way, deduction limits us to making statements about our particular 3-legged dog world. And that 3-legged dog world has no properties other than the ones that we explicitly define, and that's what we mean by top-down. So we're taking ourselves completely out of the reality game, and therefore any internally consistent statements that we make must be true. And that's the primary way that we can achieve the level of reproducibility that we talked about before. Another important thing to do to make something reproducible is that we have to define our terms very carefully. The definition of a term is a kind of assumption, and it's very simple, but it's very important. So this is a perfect example. This shows the first 23 definitions from Euclid's Elements. And he wrote it in words, but we have better things now, so we're showing it to you as a picture. So Euclid starts the book by saying, this is what a point is, this is what a line is. And, excuse me. So he didn't just do that because he was the first one to write it down. If you look at a very, very advanced geometry book today, it probably still says the same thing. The first page is, what is a point, what is a line? If you look at like an analysis or calculus book, the first page says, what's a number? What's a rational number? What's a set? What does adding mean? And it seems like overkill, but really you can't afford to skip this step. Because like we said before, we're in a top-down world, so we have to define all of our things up front. But also because defining terms is really important in all areas of your life, right? Anytime you have an argument with another person, like him, it's probably based on having 2 different definitions of a single word, right? So for example, suppose that we're arguing about what's the definition of a prime number.
Now, I say 1 is a prime number.
And I say no, obviously 1 is not a prime number. I know what I'm talking about. You don't know what you're talking about.
Well, you're the one with the math degree. I know that 1 is a prime number.
Okay, sure. So we're not going to resolve this dispute unless we know exactly what we each mean by prime number, right? So he may be using the correct and typical definition of a prime number, that a prime is only divisible by 1. A prime is a number that's only divisible by 1 in itself, in which case 1 is divisible by 1, 1 is divisible by itself, therefore 1 is a prime number. But maybe I'm feeling a little sloppy and I'm saying, okay, a prime number is a number with any 2 divisors, exactly 2 divisors. 1 is divisible by 1, no other numbers divide 1, therefore 1 is not a prime. So now we can at least agree to disagree, right? Okay, so we've talked about how to set up your proof, but we haven't talked yet about how to do the business end of it. So how are we going to make our argument? There's 2 basic methods, and we need to have silly Latin terms for these. The first one is modus ponens, or a direct proof, and the second one is modus tollens, or a contrapositive proof. And the basic formulations of them are here, in case you're already familiar. And just warning, just brace yourself, because this part gets a little bit hairier than the previous part. So, modus ponens. This tells us that given an assertion, P implies Q, and an antecedent P, then we may safely assume Q. For example, if rain implies that you'll get wet, we can all agree on that, right? Then if it's raining, we can safely assume that you'll get wet. So it seems really obvious, right? So let's look at a very slightly technical example. So if the blinking light on your laptop battery is low, if the blinking orange light implies that the laptop battery is low, and the orange light is blinking, then we can assume that the battery is low. Or to break it down, if we know the orange light implies the low battery and we observe the orange light, then we can safely assume that the battery is low. So like I said before, it seems a little bit obvious, maybe even a little stupidly obvious, but for me at least, breaking it down like this sort of makes it apparent where this could easily go wrong. So you need to have both antecedents to make this conclusion. So first of all, I might not know the implication. I might not know that the orange light has anything to do with the battery. And secondly, I might not be able to properly observe P. So perhaps I'm colorblind, or the light is on the other side of the computer that I'm looking at, or maybe there's some complicated blinking pattern that I can't distinguish between, which has actually happened to me, right? So basically we need both assumptions to make our conclusion, so you can only conclude Q if you know that P implies Q and you can properly identify P, which could possibly be difficult if P is subtle or if P is multifactorial. So moving on to the second method of proof, modus tollens, or proof by contrapositive. This tells us that if we have the same assertion, P implies Q, and the antecedent not Q, then we can safely assume not P. So continuing from the previous, oh no, we have a new example, I'm sorry. So if all humans are mortal, for example, then anything that is not mortal is not human, like a rock. A rock is not mortal, therefore it's not human. We can agree on that. So continuing now from the previous example, we start with the same assumption, and if we observe that the orange light is not blinking, then we can assume that the laptop battery is not low, that is, that the laptop battery is charged. But think about that for a second. Think about your own laptop. If there's no lights blinking on your laptop, does that really mean it's charged and ready to go? Not necessarily, no, right? There's a problem. It's not really true. So the laptop could be off, right? And then you turn it on and you see the light is blinking. Or the battery could be too low to even support the blinking. Or maybe the blinking light hardware is damaged, or something else is damaged. We don't know. So what happened here? It looks like we probably missed some assumptions in our initial statement, because we assumed a lot of things that we didn't say. We assumed the laptop is on, that it's at least partially charged, that all the hardware is in good working shape. So what I'm trying to say here is that, logically speaking, the contrapositive of a true statement should also always be true. So examining the contrapositive helps you root out the hidden assumptions that you've made. So if you would like to make an assertion and you want to make it an especially precise one, it behooves you to look at the contrapositive as well. And let's look at a more illustrative example. So the contrapositive of rain implies wet is not wet implies not rain. And again, this isn't true, because just because he's not wet doesn't mean it's not raining, right? Because not wet could also imply inside kitty, or umbrella kitties, or prepared kitty. So to sum it up, by looking at the contrapositive, our original statement, rain implies wet, we realize that it's not true because we made a bunch of unstated assumptions. Really what we wanted to say is that rain implies wet if you're outside and you're uncovered. Or an equivalent and better way to say that would be to tie it together with and statements instead of making a nested if. So rain and outside and uncovered implies that you're wet. And now we can also test out the contrapositive is true, like we asked you to do. So if you're not wet, then we can agree that you have not been uncovered outside in the rain. And that you didn't dry off. I didn't say that. So there's another one. So I think that's you.
So this is a little part where I let the audience rest a little, because I think Emily just like carpet bombed your brains with a lot of math truth. So yeah. Now there's other methods of proof and other things that we want to share with you guys, but this is a short talk, and again, we don't want to test you guys so much. So there is one interesting thing we want to share with you guys, however. So almost every formal proof or math book or science paper usually acknowledge that the reader has some certain competency, that they have a first year, in calculus, or that they have a first year in measure theory, or they know how to calculate eigenvalues. Now, by choosing one reader, you exclude another. So you're stuck with boring the more knowledgeable reader and somehow leaving behind the less knowledgeable one. And as writers, I think all of you are familiar with this problem. So we leave you with one thought about 21st century proofs. And this is from Leslie Lamport, a computer scientist from Microsoft Research. And he had a hand in developing LaTeX. And LaTeX is, of course, the math markup language that's used in math and science papers. So he has an idea for a 21st century proof. And this presents a method of writing proofs based on a hierarchical structure and naming to make it harder to prove that things are not true. So soak that up a little bit. That's actually pretty hard. So this structuring also has the implicit benefit of a drill down approach that can unravel depending on the knowledge of the reader. So to give you an idea of what this looks like, if I take a proof like an odd number times itself is also odd, and I write it as such, I can write this in 3 lines, and which is enough information for Emily to understand. Now, if you then begin to unpack each assertion and recursively add more rigor until everything is explained at its most basic level, we start approaching something like this. So now, using this method, this proof can be as simple or as complex as demanded by the reader. Now, this may not seem like a big deal, and having seen Dr. Lamport present this method at UCLA to a room packed with mathematicians and computer scientists, it was pretty astounding to see how much resistance he had from his peers. Even after their objections were met, mathematicians didn't seem to like it because they felt like they were being treated like idiots, and probably because they're afraid that they might find errors in their own proofs using this method. And also maybe they regard their own writing very highly. Now, we like the idea, but we admit it creates pretty ugly proofs. And they're almost unreadable when you look at them, if you're trying to scan for what's going on. And you can end up packing so many assertions that you actually start drilling down so deep where you get to the axioms of the system. And so at some point, you're making the thing more complicated for the reader. Now, can we use this to write scalable proofs? And can proofs and documentation be designed to automatically scale to accommodate the level of the reader? Now, Dr. Lamport believes for this method and using hypertext so that comments and details and rigor can be added at many levels into the proof and remain hidden away so that they don't distract the reader, he believes this is possible. Now, he doesn't provide any concrete examples, but it's certainly we like to see. And then between the times that we, during this conference that we're not panicking about our presentation, we've actually worked on something. And we'll share it later because it's not quite ready. But the technology for it is actually quite simple. We just use some accordion widgets and kind of start creating this drill down menu or expansion thing. But the hard part is figuring out just how much needs to be unraveled and how to present it. It's harder than it looks. So now we ask a very important question. Why do we do this talk? So we hope you got some exposure to some new and interesting ideas that will be useful, and things that you would not have otherwise been exposed to.
Right, exactly. And we also hope that maybe some of the ideas we presented, they're not usable for you necessarily out of the box, but maybe it could help you think about how to make your writing more accessible or even more credible, and at least stimulate you to think about writing and reasoning and the relationship to each other in a new way. So that's it.